Greetings all. Welcome back. We're talking about autonomous differential equations, autonomous first order differential equations. And last video, we talked about this schematic called a phase line, a way to sort of say something about the behavior of solutions to a differential equation, especially long-term behavior, without actually solving the differential equation. I want to take that one step further because we produce that phase line as some vertical slice through our slope field. So if we had a slope field, we know that every vertical slice looks like every other vertical slice. We could cut through that slope field, and that the properties of the slope field in that vertical slice readily produce what's called a phase line, which tells us about the long-term behavior of every single solution to that particular differential equation. So today I want to talk about something related to this. One can construct a phase line without a slope field. And that's really nice because, producing slope fields is time consuming and there's a lot of information there. Even in an autonomous differential equation where you know that every vertical slice looks the same, it's tedious and it takes a lot of work. So again, we're going to look at this all through the lens of this one example, and then we'll do other examples in time. So you'll see that how things change. They don't change that much. But I do need a definition here, and that definition is the following. Well, I don't need to say for the differential equation because I have it sitting right here. If we have this differential equation, y prime equals f of y, then the set, and the set is the set of all y's in R such that f of y equals 0, is called the critical point set. Of the ordinary differential equation. Okay. So in other words, the places where this right-hand side is 0, that corresponds to the equilibrium solutions. But at the same time, we say that this particular differential equation has a set of critical points, and those critical points are the places where this function is 0. Again, they correspond to equilibrium solutions, but it's just another way to sort of characterize stuff. So the properties of this right-hand side, this f of y, are going to be very important for us. So the first thing I want to do is graph f of y. So if I have y here, and if I were to graph this, I'll make this a z. For our example, if I were to graph this right-hand side, this f of z, remember that's z minus z squared, right? If I graph that guy, it's a quadratic, so it looks like a parabola. It's opening down because the coefficient in front of the z squared guy is negative. It has zeros, it's 0 and 1. So it looks like this. I'll put this as z times 1 minus z. Okay. These guys correspond to equilibria, the places where the right-hand side is 0. That's the critical point set also. So here, critical point set is 0 and 1. Okay. And everything we know about this function f of y is sitting right in front of us now. We know that here, if I drop this guy down a little bit, we know that here f of z is greater than 0 on this entire set. I'll state it this way. It's probably better if I use this bracket there. Okay. And I know that f of z is less than 0 here forevermore. And I know that f of z is less than 0 here forevermore. Okay. So I also know that z prime is greater than 0 here. Z prime is less than 0 here. Why did I put that below that? That should be like this. And z prime is less than 0 here because f of z equals z prime in our differential equation, which means the slopes of our solutions, the tangents to our solutions are all negative at that point. The tangents to our solutions are all positive here and all negative here. I can draw the phase line directly at this point by basically saying that that corresponds to one of my solutions, equilibrium. That corresponds to my other solution. Because f of z is greater than 0 here, I know I'm heading this way. Because f of z is less than 0 here, I know I'm heading this way. And because f of z is less than 0 here, I know I'm heading this way. And I have my phase line automatically drawn. And I can say now that as long as my initial value is somewhere greater than 0, I know that I'm heading to 1. Even if it's out here, I know I'm heading to 1. If I start with something negative, I know I'm heading to minus infinity. And really, with very little work, just knowing this right-hand side, graphing it, I can produce a phase line, and I can say basically what all of my solutions are doing forevermore. Nice, huh? So what can we say about these particular equilibria? And here's where things can get interesting. And I want to basically get some sense for how this works. So let's let y star be critical for y prime equals f of y. So I have an autonomous differential equation. And let's say I know a place where f of y is 0, and I'll call that y star, and that corresponds to an equilibrium solution. It corresponds to a critical point for this guy, but there's an equilibrium solution at that point. Okay. Define, and I'll explain this in a second, but you've seen this before. This is a notation for a small open neighborhood around y star. It's called we call it a neighborhood basically, for a small open set containing it. And that would be the set y in R such that y minus y star is less than epsilon. Okay. So really all that means nothing more than, say, if I had my y star here, and this distance was epsilon, then this little open set is n sub epsilon of y star. It gives me a chance to say what happens around an equilibrium. Okay, so let's say we have a critical point, and let's look at the points nearby one of our critical points. In this particular case, it will be either 1 or 0. Let's form a little neighborhood and see what happens nearby. Okay. So A if there is an epsilon greater than 0, where for all y, I want to say y0, no, for all y in the epsilon neighborhood of y star, we have the following, that the limit as t goes to infinity of y of t equals y star. Then we actually call y star asymptotically stable. Okay. What that means is the following, and here's our example. If I take my equilibrium at 1, and I say, if I can find a small neighborhood, and every solution in that neighborhood heads towards 1, then I know that this equilibrium is a nice one because if I were to start with my initial value directly on the equilibrium, I will stay there forever. But if I start nearby, I'll head towards. Now, again, for most of these guys, and for this one in particular, solutions are uniquely defined. So I can't ever meet 1 in this case. My solution that starts near 1 will just asymptote to it. I can't actually meet it. So what this guy is saying here is that in the limit, this is an asymptote, right? In the limit, it's y star. It'll never be y star, but it is. Then we call this guy asymptotically stable, or sometimes we call it a sink, because all the solutions nearby head towards it. One example of this would be if you had a pendulum, a damped pendulum, and you start the pendulum with no initial kick to it, and you started perfectly vertical, it would stay there forever. However, if you gave it just a small kick to move it, so you get a small sort of movement, periodic motion back and forth. It's not periodic though, is it? Because slowly it'll die down to 0. Okay, if I give it a larger kick, it's still going to slowly die down to 0. Okay, we call that equilibrium at the bottom there asymptotically stable because all the nearby solutions are heading towards it. Okay? That's a classification of a particular equilibrium, which is going to be important for us because if we have a mathematical model and we want to be at a steady state, but we don't have good enough resolution to hit it, right? What does it mean to have an equilibrium at y equals square root of 2, and then on a computer you say, hey, let's set my initial value to square root of 2, and it says, I can't do that. I can set it to 1.14 whatever square root of 2 is, up to 8 digits or up to significant digits or up to 16, but it can't hit an irrational number perfectly. If you're at an asymptotically stable equilibrium, that's okay. If you're at an unstable one, that's a problem. But anyway, here, we call such an equilibrium like this guy at 1 asymptotically stable because all the guys nearby it head towards it. B, and this is not really completely accurate, but this is a great way to do it right now. If there is an epsilon greater than 0, where for all y an element of the epsilon of y star, the limit as t goes to minus infinity of y of t equals y star, then we call y star is unstable. Or sometimes we call it a source. If we look at 0, if I start my solution at 0, perfectly at 0, I will stay at 0 forever. But if I start my solution at any number that's not 0, no matter how close to 0, 0.00000001, at that point, I have a positive f here. At that point, I'm moving away, even slowly at first, doesn't matter. At that point, eventually I'll head to 1. At that point, I'm moving away from 0. In backwards time, I'm moving towards 0, but in forwards time, I'm moving away. That's the same thing as saying right here. If I start with the smallest negative guy here, eventually I'll head out towards minus infinity. 0 is an unstable equilibrium because if I just barely miss 0, I won't stay near it. I'll go away forever. One way to characterize that for us right now is to say that if I go in backwards time, in other words, if I travel towards minus infinity, I will be heading towards. So unstable equilibrium at 0, an asymptotically stable one at 1. There is a third quality in which sometimes we have something which is moving away on one side and moving towards on the other. And we'll do an example very soon. That is sort of a combination of both of these guys, and that's actually called semi-stable. But we'll talk about that next time. For now, thank you very much for listening, and we will speak again very, very soon.